Okay, in this video we're going to look at momentum collisions in 2 dimensions. So, what you need to remember for this is that momentum must always be conserved, but not just in the same in one plane, but in all planes. So let's talk about that very specifically. So, say if we have a ball coming towards another ball of equal mass, and striking it obliquely, then what you'd expect is kind of a snooker ball kind of situation, that they go off at an angle such as that to each other. And we could actually suggest we could put a value of theta for those, theta 1, theta 2, just to give them numbers so we can discuss them more readily. So what we've got here, so this is ball 1, that's ball 1, that's ball 2. So that's ball 1 after it diverts off. So the ball travels and then bounces off in that direction. Right, so what can we say about this situation that we need to make notes on, really? Well, as we would expect, this is an elastic collision, so we would expect momentum to be conserved. Now, that means the momentum must be conserved in every orientation before and after the collision. So, the momentum here, let's give this numbers to make it clear. So, say 1 kilogram again. 1 meters per second. So the total momentum of the entire situation is going to be 1 kilogram meters per second. Quite simply because ball number 2 is not going to be moving, hence it's got no velocity, hence no momentum. So if we add the momentum in both situations up, we'll get a total momentum of 1 kilogram meters per second, which we're going to assign as a positive value. Right, so for this collision to be correct, then what we would expect is the momentum in that orientation to be conserved, which means that after the collision, the total momentum in this direction must be conserved as well. So we would expect the total momentum in this direction to be conserved. So, how is that going to happen? Well, quite simply because if we look at each one of these situations, this one and this one, so ball 1 and 2 after the collision, you could split both of these up into vectors, into a vector resolution. So if it's got the velocity up there, and then you've got it resolved into a horizontal and a vertical component, which has a velocity in each orientation for both. So that's the velocity to vertical and horizontal parts of that respectively. Same thing you can do with the one ball number 1. You can suggest that it has a resultant in that direction, which is made up of a vertical and a horizontal. We'll call that V1. So that's that is vertical. That's horizontal. That's vertical. That's horizontal. So what we've got here is a situation where we can have a look at these vectors and see what we can say about them. Well, we know full well that this velocity here times by a mass will give the horizontal momentum of ball 2 after the collision. So if we then add the momentum of ball 1's horizontal velocity, so the velocity here will give a momentum of ball 1 in that orientation. So you've got the velocity making a momentum, velocity making a momentum. Those two momentums added together would have to equal that there. So if I write that in, so essentially the momentum in this direction would be equal to hv2 plus hv1. That must be the case. If it wasn't, the momentum wouldn't be conserved. Okay, and we would expect those to then also equal the 1 kilogram meters per second. All right, there we go. So that gives us a complete horizontal resolution on the momentum there. What about the vertical then? Right, so the vertical is exactly the same. However, you need to consider the fact that what is the vertical momentum before the collision? So if we think about the vertical momentum in this orientation before the collision, well, you ask yourself a question, is it moving upwards? No. Is it moving downwards? No. So therefore, there is literally no momentum in that orientation whatsoever. So there's no orientation. So that's 0 kilograms meters per second. And so we would expect, if we are to conserve momentum in every plane in 2 dimensions, as we suggested, then after the collision, we would expect the same momentum, total momentum, to be observed. Okay, so how can that work? Well, the only way that would work is if this value and this value, when used to work out the respective momentums, they must be equal and opposite. Well, you might be saying, well, how can that be? Well, it must be equal and opposite because if we assign this as a positive value, if we assign that as a positive value and that as a negative value in that orientation, then we would expect that since there is 0 before, there must be 0 after, because you can't gain or lose momentum in any direction in that regard when we've not got an external resultant force, which we don't have here. So as a result, we get a balancing of the velocities if they were the same mass. Okay. So the concepts I'm showing you there are very, very important, and we'll hopefully put them into perspective in a question setting in the lesson.